Let's take a look at this. So this first one, we have a ball. It's struck at t equals 0. Basically, we're looking at projectile motion. It reminds you it follows a parabolic path, and it gives you these 5 graphs. I'm going to ask 2 questions. Which graph represents the horizontal velocity? All right, number 1, horizontal velocity in projectile motion is constant. Remember, gravity only pulls this thing down. There are no forces in the x direction, so the horizontal velocity cannot get affected. So specifically, not only is it constant, but we know what it is. It's just v naught cosine theta. Now the vertical velocity, well, gravity is going to pull that thing down. So the vertical velocity is going to start out at v naught sine theta, and then we're going to subtract 9.8 meters per second for every second it's in the air. So horizontally, we have a constant, and then vertically, we start out with a positive, and then we linearly decrease because of that negative 9.8 slope. So number 1 is E, and number 2 is in fact D. All right, this one they're tricking you because they label this velocity. Remember, velocity is not a force. Velocity is just a piece of information that you are moving up this ramp, and it asks you questions about your acceleration up and down the ramp. Now, we went into lots of detail about drawing free body diagrams for this guy, but we know that the normal force is perpendicular, gravity is straight down, but gravity's components, well, mg sine theta is down the ramp, mg cosine theta is into the ramp. So as far as looking at the acceleration, remember, velocity is not a force. It is not on your free body diagram. The acceleration is actually always just down the ramp. Okay, it's specifically g sine theta down the ramp. It doesn't matter whether you're moving up the ramp or down the ramp, gravity's component is going to be down the ramp. So as far as the acceleration is the same moving up and down. Now, if friction was involved, then it would be different. On the way up, meaning as the object is moving up the ramp, friction would be down the ramp, mg sine theta would be down the ramp. They'd be working together to slow you down. As the object then slid back down the ramp, then gravity would be making it go down the ramp, mg sine theta, but friction would be up the ramp. So in the frictional case, friction always is going to oppose the motion here, where mg sine theta is always down the ramp. Then our acceleration rates would be different. But if we don't have friction, and it says frictionless, then in this case, mg sine theta is down, and so both cases going up and down, the acceleration is the same. Okay, this is, once we give this pulley some mass, then we have to have a torque to spin it. And if we have to have a torque to spin it, we have to have one of the tensions bigger than the other. And remember, if we're going to spin this thing clockwise, T2 must be bigger than T1. And so we end up getting that. There must be some unbalanced torque to end up spinning this thing. This is our classic center mass equation, right? We know that what we're going to do is we're going to take each mass, multiply it by its position, and add it to the other combos. And so what happens is the bigger the mass is, the more that position matters in terms of the overall center of mass, which is really just the average position of all the masses. So we have some coordinate system, and this one's at 0, this one's at 3, and this one's at 5, and then they each contribute a certain amount, and then divided by the total mass to get then the average position of the mass, which would also be the equilibrium point, which is also known as the balance point, which is also where, if you put your finger, there would be no net torque on the system because you're putting your finger on the center of mass. Which is an equivalent unit of momentum. Okay, so now remember, momentum is mv. So the units of momentum are kind of stupid. There's not a special word for it, like joules is to energy and newtons is to force. Momentum is just kilogram, meter per second, right? And mass times the velocity. But that's not a choice. But you also got to remember that the change in momentum, which we call the impulse, well, that just says how big is the force and for how long. So also then a change in momentum, which has to have the same units as momentum, has to be a Newton second. Applying a force for a certain amount of time gives you then a certain change in momentum, Newton second. All right, this one is a whole double triple thing. We know that the height fallen, remember that's not the actual height function, that's the distance you've fallen function, right? And it's quadratic. So h is proportional to t squared. So if you double the time, you quadruple the distance you have fallen. So A is only fallen 1/4 of B if B falls for double the time. So classic kind of double triple. 8 is a circular motion question. You're taking this mass and you're going around a circle. That was a terrible circle, but we'll take that. And so we start out with forces. F equals ma. The force causing circular motion is tension. And then we can replace A by v squared over r, or we can replace it by omega squared r. In this case, we have information about the velocity, or actually we want the velocity, so let's leave it as v squared over r, and then you're just kind of plug it in. Remember, the tension in the string is right here. They tell it to you. They tell you, hey man, the biggest this string can handle is 10 kilograms of weight, which is them telling you, oh, it can handle 98 newtons of force. Remember, mg. Number 9, all right, we got this collision. You think collision, you think momentum. Momentum is always conserved in collisions. Now, if it happens to be elastic, then we'll conserve energy as well. But in general, we just conserve momentum. And so this collision, we say momentum is always conserved and kinetic energy is sometimes conserved if it's elastic. So this is a calculus question, twofold. One, they kind of give you this weird workaround that you want the velocity as a function of time, which is weird because they give you the force. However, the force, so right, F equals ma, the force is bt, so then you can find the acceleration as a function of time. But then you're like, oh, I know this one. The velocity is just the accumulation of acceleration over a time period. So we can integrate acceleration to find velocity. And at this point, you can be given any of these things: force, acceleration, velocity, momentum, kinetic energy, power. You can be given all of those as a function of time. Remember, once you see this guy right here, F equals bt, you cannot use any of our standard equations. That says that the force is some linear function. Once it's a function, you got to think calculus. So they give you force, that finds acceleration, and with acceleration you can integrate to find velocity. All right, 11, they're going to trick you on this one. They're going to make it look like, oh, there's these 3 blocks and there's all this stuff. There's no friction. You can think of this whole thing right here as just one big block that's 6 kilograms. And all you're doing is pushing it. And you want to push it at a 2 meter per second acceleration. So 6 kilograms that want to be accelerated at 2, boom, you got to push it at 12. That's it. You're not talking about the internal forces, nothing. You don't even know when you push this thing that there are 3 boxes. You just know that you're pushing 6 kilograms worth of stuff. All right, an electrical motor provides 0.5 watts of mechanical power. Remember, watts is the unit of power. Watts is joules per second, and they want to know all the time. And so the first thing you probably write down is that power is work over time. Again, power is work over time, and work can be lots of things. Work can be accelerating something. So the work might be the change in kinetic energy of like speeding up a car. It might be stretching a spring where the work is 1/2 kx squared. But in this case, the work is lifting something. So the work is mgh. The work you do changes the potential energy of something, and so then the power is just mgh over t, and then you plug in. All right, we have a block here with potential energy. It zooms down here with kinetic energy, and then all that turns into friction. And so we want to figure out how far the block slides before coming to a rest. Well, at the beginning, it's all mgh, and at the end, it's all heat, meaning the work done by friction. So we just set those things equal to each other and solve for the d, at which it would take to convert all of that to here. Now I get it. I understand. Potential went to kinetic, and kinetic went to heat, but we can skip that secondary piece. Just go from the beginning all the way to the end. All right, 14 and 15 are very similar questions. This is the graphical version and this is the calculus version. We are looking for the acceleration to be constant and non-zero. We're looking at a velocity versus time graph. The slope on this graph is acceleration. So here, the slope is 0, so the acceleration is 0. And here, the acceleration is 0, right? The velocity is not changing. This little weird spot there where it's curvature is some non-constant. But look at RS and ST. Those are where the slopes are constants. That means the acceleration is constant and non-zero. So we're looking at those guys. Here, instead of looking at a graph of velocity versus time, now they actually just give you this function of velocity versus time. But you just take the derivative to find the acceleration and then plug in 2 seconds to find the acceleration at that moment. All right, you see this, boing, 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 boing. Right away, you will think simple harmonic motion, right? You know this is a spring bouncing back and forth, okay? Which of the following is the upward velocity the greatest? So you're looking for a positive slope, right? Upward velocity, positive slope, and the first time, and it's right there. Again, we know that an object in simple harmonic motion is moving the fastest at equilibrium. Once it goes past equilibrium, it starts to slow down because it's compressing or stretching the spring. And before that, well, the spring is still compressed or stretched. It's moving the fastest when it gets back to equilibrium, and that's that middle value. Okay? And in this case, what's the spring constant? Again, this is our classic formula for the period of a mass on a spring, where the mass is in the numerator and the spring constant is in the denominator. If you look at the graph, you easily can find the period. You're just going from one peak to the other peak, right? That's a full period. Or you can just go from here and go down. That's also a full period. And figure out the time. And then they gave you the mass, and so you're just doing a little algebra to find K. All right, so this one's also, they're trying to trick you. Identical forces act for identical times, okay? So we agree the same force is being applied for the same time period. That will cause the same change in momentum. Now, it will not cause the same change in velocity. If I apply the same force for the same time on a small thing, I'm going to accelerate it and I'm going to get it to a big velocity. A big thing to a small velocity. But the bigger mass, smaller velocity, smaller mass, bigger velocity, but the change in momentum is the same. If F and T are the same, the change in momentum is the same. Don't get momentum confused with velocity. All right, this is the parallaxis theorem. Again, they're trying to trick you. Don't focus on how far the pivot is from the right edge, even though that's what they gave you here. That's a trick. Always, always start in the center and figure out how far the pivot is from that. Now, in this case, they're the same. It's L over 4 in both cases. But when you use the parallaxis theorem to find the new moment of inertia, if you move the pivot, this guy is always the middle one. Start in the middle and go out to the pivot. How far you move the pivot from the center of mass. All right, this is the definition. We know this. This pops up multiple times. I think another time even on this worksheet. The potential energy is the accumulation of force. But again, it's the negative version. Just think of springs. Energy is 1/2 kx squared. Force is negative kx. The force is the negative derivative of potential. Thus, the potential is the negative integral of force. So all we got to do is take this guy, drop the negative sign, and integrate kx cubed and get 1/4 kx to the 4th. Remember, this is a weird spring. This is not a Newton's law spring, or a Hooke's law spring, excuse me. This is a non-linear spring, which will then give you a different energy instead of 1/2 kx squared. It's going to give you, in this case, 1/4 kx to the 4th. Right, this is just classic simple harmonic oscillator, right? In an oscillator, we know F equals ma. The force on the spring is negative kx, and we replace a by x double prime. And remember, x double prime in the calculus world looks like that. These two things are the exact same thing. This is the calculus way, and this is more the physics way. All right, this is an object moving around the sun in an elliptical orbit, and we know that when you're closer, you're moving faster, and when you're farther away, you're moving slower, and that goes back to conservation of angular momentum down here. We know this to be true, and so we just answer questions, okay? Number one, the comet's kinetic energy is the biggest at 2. Well, yeah, we just decided. It's the closest at 2, so it's moving the fastest at 2, so it's got the most kinetic energy at position 2. What's the ratio? We know that the ratio is the exact opposite. If it's 10 times farther, it's 10 times slower. So the ratio at 2 versus 1, the position at 1, since it's 10 times farther, it's going to be going 10 times slower. But the ratio of the forces, well, now we're looking at the gravitational attraction. Well, it's 10 times farther. Look. Well, now it's an inverse square law. The radius is in the denominator. So if you multiply that guy by 10, you multiply the force by 1 over 100. Okay, this one. We know that the frictional force equals mu n. In this, right? This is the definition of friction. Friction is mu n, and in this case, n is mg sine theta. I didn't actually go through the free body diagram and the x hat and y hat, but just remember, think about it. Normally, when a box is just chilling, mg is down, normal force is up. But in this case, you're actually pulling up on this thing. So F sine phi, that's how much you're pulling up, which is helping the normal force. So the normal force is predictably mg minus F sine theta, smaller, a little bit smaller. And then the frictional force is just mu times that. This is the whole equation if you actually were trying to write out the x hat equation. Don't let them try to trick you. They want the tension in the string. Anytime you want tensions, focus on one object and one object only. So just look at that guy. Tension's up, mg's down. Bingo. Move on. 27. Okay, this one. I like this question because it gives you all this information about distance, velocity, and it wants to know acceleration and forces. Like, wait a second. Normally I find with a distance and a velocity, I can use the v squared equation to find acceleration. Well, yeah, that's what you do. But then you just go one step farther. You wanted to find the force. So normally we think F equals ma and try to analyze this, but you're given kinematic stuff. You're given distances and velocities. So just use the kinematics equation of v squared to find the acceleration. And then once you know the acceleration, well, if you have something that was 0.2 kilograms and it accelerated at 500, you can then say, well, it must have had 100 Newton force acting on it during that time period. 28, you got a collision. Once you see collision, you think, oh, has to be momentum. So let's conserve momentum. P1 equals P2. This is me looking at before. Okay, this is the 1500 moving right at 4, 3000 moving left at -3. That's the initial momentum. They stick, because they tell it to, which is completely inelastic. And then they travel as one 4500 thing at what? So you just conserve momentum. You get -2/3, which does mean it's going left, but they say speed, so they're just ignoring the fact that it's a negative because it's left. And so then you just circle the answer. All right, this one, we want to know the torque. We know that torques are forces and lever arms, and this is kind of the picture you got going on based on this meter stick and where they're at on this thing. So this is a very key piece of information that you'd have to draw yourself and then think about the torques. You got this 1 kilogram at a 0.4. Remember, there's no angle because they're all perpendicular. And then you got this 0.5 at a 0.6, and this difference is the torque. You don't even need this part here. Right, that's what torques cause. Torques cause things to rotate. They just actually want to know the torque. They didn't want alpha. Usually they ask for alpha, and then you'd write the whole thing, but you actually just are focused on the left side of the equation and just find the net torque. All right, this is a simple harmonic motion. We know that that looks like this. Negative kx equals ma. We can solve for a. How do I know to do that? Well, look at the graphs. You want a as a function of x. So just find your classic differential equation. Negative kx equals ma. Divide by m, and boom, you got an equation that says a as a function of x. This is a negative line. Negative line. All right, this was like our projectile motion test where we were like throwing ball 1 and throwing ball 2, because what we want is we want to figure out the time when the two balls pass each other. Passing each other is the same thing as hitting each other. So we got to write an equation for 1 and 2. Okay, 1, there's your drop equation. It's at a certain height h, it's going to lose 1/2 gt squared, and that's the height as a function of time. Where number 2 is thrown up from the ground. So it's from the ground, so no initial position, but it's got a v naught t for its initial velocity. And so all you gotta do is set h1 equal to h2. That's what it means to pass each other, which is the same thing as colliding. You want them to be at the same height at the same time. So set them equal, cross those off algebraically, and boom, you're done. That's the time at which they would hit. If you want to know the velocity at which you could hit, then you'd have to go to like v equals v naught minus gt and stuff like that. This is what I was saying earlier. Earlier they gave you force and they wanted to find potential. Here they gave you potential energy and they wanted to find force. So all you gotta do is take the negative derivative, and we know equilibrium means when the force is equal to 0. So take the negative derivative of this and then set it equal to 0. Again, we'll find the force function and find out when the force is equal to 0. This one of my least favorite questions on this because of this. Speed and speed. Now remember, most of the time, the velocities are vectors. And so, yeah, you would do Vf minus V naught. This actually makes sense most of the time. That is the answer. But it's not, because they define Vi as speed and Vf as speed. And so if you're going 10 meters per second down and 8 meters per second up, the difference between those velocities is what momentum needs. And since they're speeds, we actually add the numbers together. Remember, if this is 10 and this is 8, there's actually a difference of 18. And so we actually have to select C as our answer, which is ridiculous. It's almost always B, but they trick you because they define these V's as speeds rather than velocities. All right, 2 more. All right, number 1, from now on, you do have to recognize that guy is circular motion. Okay, that's circular motion. Think about X, if you bounce back and forth, boom, 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 X-wise, and you did that motion at the same time vertically you were oscillating, you actually just do this. I'm bouncing back and forth left and right, but I'm actually doing it at the same time vertically. This is circular motion with a radius of 5 right there. That's the amplitude of our motion. This is like unit circle stuff. And then also if we took a derivative, then we'd get 15. So think about the speed being 15. And again, it's constant speed because they're both the same. This is something I do need you to know. The BC kids would know it a little better because they studied projectile motion more than AB, but that is circular motion from a parametric equation standpoint. All right, that was 2012.